We are heading towards the next presentation, which will be presented by Andreas Klinger. And he'll be talking about an interesting topic, how to toughen epoxy-based carbon fiber reinforced composites. So the title is Block Copolymer and Core Shell Rubber Hybrid Toughening of Epoxy-based Carbon Fiber Reinforced Composites. Let's welcome the speaker.
Mr. Chairman, thank you. I'm Andreas from the Institute for Composite Materials in Kaiserslautern, Germany, and I will talk today about epoxy-based carbon fiber reinforced composites and toughening by block copolymers and coarser rubber particles. First of all, I will go through a short motivation and the background for the project, explain a little bit more about the goal of the study, toughening in general, experimental section, results, and finally conclude. I brought you two examples which are very famous, I think. First of all, the new A350 and the ULR version. A couple of weeks ago, it was delivered to Singapore Airlines in this ULR version, which allows you to travel about 20,000 kilometers without refueling. And this is majorly driven by carbon fiber reinforced composites because this airplane is made out of 53% of this material. Even 90% of the primary loaded structures are made out of CFRP, right? Another example is car rim, in that case from the BMW M4 GTS, using carbon fiber reinforced composites in these parts allows you to get a higher cornering stiffness so you can go even faster through the corners. The problem is if you think about hitting the trottoir with the rim, right, it might be broken immediately. So what can we do about that? The problem of CFRP or epoxy-based CFRP is that it's very brittle. We need to improve the toughness and especially for aircraft, for example, to make thinner laminates and further reduce fuel consumption and so on. So maybe we can one day travel around the world with one fuel tank. In the morning we heard from Professor Ritchie already about the extrinsic toughening, and that's actually the approach we are following as well. Toughening of polymers, epoxies can be done by adding second phase modifiers. They work in different ways. So for example, rubber can bridge a crack, right, and close the crack mouth more or less. Then we have more inorganic or rigid particles which lead to a crack deflection mechanism. In the end, everything is related to the plastic zone size. So if we can increase the plastic zone size, we can increase our energy release rate of the material. The goal of the study is if you take a look at this graph, on the x-axis there's the normalized stiffness, and on the y-axis you can see the normalized energy release rate. First, a look at the compliant modifiers taken from different literature resources. You see that we are usually decreasing the stiffness. It's a drawback, right? But we are can strongly increase our energy release rate, our fracture toughness. On the other hand, inorganic rigid particles lead to a strong increase in stiffness. However, the toughening efficiency is limited. Nowadays, there's a new approach using hybrids, and that was why the study was more or less inspired by hybrids to use inorganic and compliant modifiers to balance the loss in stiffness, but to get still a quite proper increase in fracture toughness energy release rate. Toughening by block copolymers and coarser rubber particles has different other advantages, which I will show you in the next slide. However, we will expect to be somewhere here in that area, because both modifiers are rubbery modifiers, so there won't be any effect on the stiffness in that sense. The block copolymers we used is a triblock copolymer made out of, so block copolymer is a material, or actually, yeah, it's one material made out of two or more constituents. polymers which are usually not compatible, but you can, via chemistry, merge these polymers and create a macromolecule which has, for example, an epoxyphilic and an epoxyphobic part. And now imagine you put that in your epoxy, you will have, driven by thermodynamic forces, some kind of phase separation, right? This phase separation is, for example, shown here. Yeah, so this is the nice thing about copolymers. You don't have to have any kind of dispersion efforts. The other part is the coarser rubber particles, which are nowadays available in master batches. You have a core, which is a rubbery core, and a shell material, which is adjusted to your resin you are mixing the materials in. No dispersion efforts, no agglomeration, which we usually have when you think about nanoparticles as a powder form. You have to have a lot of shear forces to break those up. And then, additionally, due to the special construction of those materials, we don't have a depression of GG. The base material I used was bisphenol A-based resin, cycloaliphatic anhydride. That's especially good for having longer pot life, to think about filament winding and so on. So no snap curing here. We used aerospace certified fibers. In that case, it was a Tenax fiber. Yeah, and I have given some properties from the neat matrix, where you can see it's a quite brittle system, well, which has already quite some elongation in the unmodified version. Where's the fracture toughness? There. So 0.6, which is far away from 450 megapascal, what we heard in the morning as well from Professor Ricci for metals. So what happened? We mixed the materials, casted them in glass plates, obtained our samples after curing them in the oven, and characterized them via different methods. Processing of the laminates was, well, not done similarly, but closely related. We laid up the fibers in unidirectional direction, 12 layers, hand laid up them, so resin was put on single ply, and then another ply was added, and so on. In the end, we obtained a laminate thickness of about 3 millimeters and 60 volume% of fibers. The materials were autoclaved and afterwards tested. We did different systems, a couple of block copolymer toughened systems, a couple of coarser rubber toughened systems, and a couple of hybrids. And the total amount of modifier was varied in between 0.5 and 17 volume%. That will be important now, as you can see. In this graph, you see the flexural modulus. On the x-axis, you can see the concentration, all over concentration. And what is important is that you have more or less, no matter what modification you use, it simply depends on your rubbery phase. Your stiffness is decreasing. Additionally, well, it could be nicely modeled by using the Halpin-Tsai equation, which is for sure fitted in the end, or is a kind of fit what you can use. The same works with the fracture toughness. This is all from the matrix, to point out. It doesn't matter what kind of modification you use. Is it block copolymer, is it a coarser rubber, or a hybrid in the end? You get a certain increase in fracture toughness, and then it bottoms out. To see the effect of these materials on the laminates, yeah, we manufactured the laminates as I've shown you, and we performed different kind of tests. We're following, in this case, for the mode 1 DZB test, the European standard 6033, which is also used by majorly by Airbus. And the results are shown here. On the x-axis, you see again, this is a special graph. So on the x-axis, you see the energy release rate of your matrix. On the y-axis, you see the steady state propagation energy release rate, the steady state propagation of the energy release rate of the laminate. And there are different things to point out now. First of all, if you take a look at this point, at the neat reference, to better see that, I added those dashed lines so we can follow the kind of excess, what you would usually expect. Yeah. So if we have the neat reference, we test that in the matrix, we get about 100 joule per square meter. If we test that in the laminate, we get excess of threefold, more or less. And this is related to additional mechanisms, as some of us have learned in the summer school as well, by fiber bridging effects and so on, which are introduced in the laminate. The other samples, as you can see, so now you add your modifier. What happens? You increase your fracture toughness or your energy release rate because you have those additional mechanisms in the matrix. At a certain concentration, and I want to point out this one, which is coarser rubber, 8.8 volume %, and this point, which is the block copolymer toughened system, your slope is leaving this 2.0 slope. It bottoms out. And that is effect introduced by the fibers in the end, because you have 60 volume % of very, very stiff fibers in your system, and now you increase your plastic zone size by those additional particles, and suddenly, hey, they are restricted by the fibers which are present. Even more interesting is that due to a hybridization, we suddenly end up here. So what I would expect if I add more of this materials, that we follow this path, right? Okay, how much left? 5, okay. So, yeah, so what did I do? We took a look at the interface, because that's one of the other factors which can influence this kind of trend. As you can see on the left side, we have a neat reference CFRP sample. We have some kind of bonding of the matrix, which is for sure required and expected, because it's a fiber with an epoxy sizing, so yeah. On the other hand, same magnification, you see that we have a much severe or stronger matrix adhesion to your fiber, besides the different look of your matrix. As you can see, we have a lot of matrix adhesion to the fiber, as you can see in this higher magnified image. And that might be responsible for this increase in fracture toughness. To have a small digression on the micromechanics, we took a look at the particle distribution and the particle size and the interparticle distances in these laminates. And what we found is the smaller, so first of all, on the x-axis you have your interparticle distance divided by the particle radius, right? So a ratio out of this one to that one. On the y-axis you have your energy release rate. So the smaller you make the interspacing between the particles, the higher your energy release rate comes. What you do is you probably change locally, in between the nanoparticles, your state of stress from a plane strain condition to a plane stress condition, which additionally, further to the making use of the particles in terms of cavitation and so on, you make use of your matrix by allowing the matrix to yield. Interesting was when we added some more data from the literature that we followed a similar trend, right? And there is a percolation theory by Wu, which is more or less explaining this behavior. And we can see that even in our CFRP. So what you see here is a kind of apparent brittle to ductile transition. What we can make out of that is you only need to add more and more particles into your system, which is already possible now by using master batches, and you can activate your matrix rather than only be a carrier for your particles, right? So the results out of this study where we have a similar effect of block copolymers and coarser rubber particles on your stiffness and on the fracture toughness. We have, due to the hybridization, an improved fiber matrix adhesion, and the interparticle distance and particle size ratio are important properties to be considered for further processing or further research in that area. Yeah.
Thank you very much. Speak, please.
Can we look at slide 17, please? Okay, you show us the energy release rate, the critical one.
Yes.
On both slides, on both axes, but And you use this formula W over B delta A. Why didn't you use ASTM or ESO standard to?
I don't know. At the beginning, we simply worked with this standard, and afterwards I learned from the other standards which are available. In the end, it does not really matter because you get an average value of your correct propagation value, right?
Is this an initiation value?
No, this is no initiation value, this is a propagation value. So initiation values were obtained, but they are not presented in terms of nonlinearity. When you get your force displacement curve, you can also take a look at the curve when it leaves your...
Is this the asymptote? Or, I mean, you have
This is it.
a GR curve, so you have an initiation value, and then you have an increasing in the R curve, and then you usually settle down.
Exactly. No, so W is the energy below your in your force displacement curve, and you relate it to the to your sample size and to the correct propagation delta A. Right? So it gives you the same values as more or less as the ASTM and the ISO standards.
Thank you.
Any more questions? If not, then we'd like to thank the speaker.